All right. Good afternoon. We're going to talk about in the next couple of weeks, we're going to go over correlation and regression analysis. This is part one of 2 lectures. So our goals are to, we're going to interpret bivariate correlation and regression analysis. And secondly, our hope is that you'll be able to better understand the concepts of sensitivity, specificity, receiver-operator characteristic curves, and event probability analysis. These latter concepts will be talked about next week in the context of logistic regression analysis. What we'd like you to do is also, you get the chance, watch these videos. I've got a series of videos here as well as for next week that I've identified on YouTube that I think will help reinforce some of the concepts and also cover some things that we don't specifically talk about in this lecture. So one of the things last week, or the last time you should have had a review in previous weeks of selecting a statistical test. And so here's just a little decision tree that I found on the internet, and what we're going to talk about first is looking at correlational data, and then we'll get into, after that we'll talk about linear and multiple regression. Here's another flowchart that I put together to kind of help you think about when you're looking at choosing a statistical test or when you're reviewing a manuscript research article. Helps you understand what test they chose and if they're correct. So the first thing, if we go back to, is you got to think about what is the nature of the research question, what's the hypothesis, and if they're choosing to if they're looking at relationships between an independent and dependent variable, then that's going to take them down the road there where they're looking at either simple correlations, or if they're looking at predicting a dependent variable from a number of independent variables, then that leads you to some form of regression. And it depends on what type of independent variable that is, whether it's nominal, ordinal, or interval ratio, as well as certainly the number of groups can have an impact. And so this flowchart can kind of help you think through some of that. So what we're going to talk about in part one is we're going to go over Pearson's R correlation coefficient and Spearman-Rho. Spearman-Rho is the non-parametric version of a correlation when you have ordinal level data or non-normally distributed continuous data. Then we'll talk about simple linear regression, which is built on the concept of correlations. And then we'll talk about multiple linear regression. In the next week, we will review the concepts you see I've listed there, and we'll spend a fair bit of time talking about logistic regression. All right, so I imagine many of you are familiar with a correlation. A correlation is looking at relationships, and there's some important concepts you need to understand. And first is in terms of what is the x and what is the y axis. This is something that I always, even when I went through a statistics class, took me a while to really wrap my head around and understand, just to remember. But your x-axis is the horizontal axis here, and then your vertical axis is your y-axis. And so the y-axis is your dependent variable. This is what you're trying to explain or predict or look at the relationships with these independent variables. Another term you may see with the y variable is the explained variable, the response variable, the predicted or outcome variable, and this is especially in regression analysis, and also this term regressand, which I'd never heard of. And then the x-axis, these you can think of your independent variables, your explanatory variables. Also in multiple regression, you might be variables you're trying to control for, or more commonly, they're predictor variables that you're trying to predict some outcome based on the scores from the independent variable and the regressor. Very important concept, and I know we've talked about this before. Correlation does not equal causation. A correlation or relationship between two variables only indicates that there's some sort of relationship and possibly the strength of that relationship, but it does not prove causation. So what is a correlation? A correlation is a linear relationship between two variables. And a correlation coefficient measures the strength of that relationship between the independent and the dependent variable. The parametric version, when you have continuous data that is normally distributed, is what we call a Pearson's R correlation coefficient. Sometimes referred to as the R. You'll see that in italicized as or the non-parametric version is a Spearman rho. So a perfect correlation is as one score goes up, the other one goes up. Perfect late line, and it goes positive. Goes from the lower left-hand corner to the upper right-hand corner. A negative is the opposite. Now you can have low degrees of correlation, both positive and negative. You can have high degrees, and that usually has to do with how tightly spaced the dots are on a scatter plot. Or you can have no correlation at all. And so what we typically will use are scatter plots or scatter diagrams to visually check for linear relationships. Many times before you even start doing statistical tests, such as a correlation, you may visually examine the relationships between the variables using scatter plots, just like these. So when you have correlations between continuous variables on a continuous scale, that's a Pearson R. And we report those as an R value that you can see I have listed here. And we can look at the strength of that relationship, or you can also consider maybe the effect size as how strong that correlation is, with a low or weak correlation being an R value of 0.2 to 0.4, a moderate being 0.5 to 0.7, and anything above 0.7 would be a high or strong correlation. And we can see some examples here where you have a perfect positive, which would be a 1. A perfect negative would be a -1. Okay, so that's a perfectly negative correlation. It's perfectly positive. Then you can have something in between those. And you can see how, as they're higher, stronger correlations, the dots are more tightly wound together. Okay. So types of correlation, again, you can have negative, whereas X increases, Y tends to decrease. A strong positive correlation, as X increases, Y increases. Where you have no correlation, where you can visually, we don't even need to run a statistical test, and we know that there's no correlation there. And you're also going to have some other, where you have non-linear correlations that you'll sometimes see, and sometimes we can use different types of analyses to examine those relationships. And then you can see over here similarly, so if we look at a strong negative correlation here, we have an R value of -0.91. And then here is a strong positive correlation, which is an R value of 0.88. And you can see what would be a weak correlation might be an R value of 0.42, or a nonlinear correlation right here. There's a few assumptions that go along with correlation analysis that you need to be familiar with, because you're gonna read about them when you're reading research papers. And one of the first keys, as I've already mentioned, is they need to be if you're running a Pearson's R, they both need to be continuous variables that are normally distributed. There needs to be independence of observational pairs between them. And meaning there should be some, they're not paired data. And there also should be this term of homoscedasticity, which looks at the variability in the scores of the independent variable, and they're basically saying that variability is consistent across the variables. So what we can do is we can see that in this figure over here, that they're not all a straight line, a straight dot up forward, but there's a little bit of variability, but they're all varying in the same direction. Whereas this one they're not quite varying the same way. Okay, and so you can actually see that, and also there are some statistical tests that can test for that in our software packages. So here's an example of a article I pulled up on the internet as I was preparing this lecture. And the research question in this particular study was that is there a relationship between 4-hour PCA ratios and 24-hour opioid consumption in children undergoing scoliosis surgery? And so here I've pulled the initial part of the abstract. You can see the title there. And what you're seeing here is they're actually writing their hypothesis right here. The authors hypothesized that the PCA ratio is able to predict morphine requirements in the first 24 hours. So if I read that, when I'm looking at their analysis or their results, I'm probably going to look for some sort of a multiple regression. However, many times before they get to doing a multiple regression, they're going to do simple correlations and many times present that data in their results section. So what I did here is I wrote out what a potential question, I pulled this from their results. And what they said was there was a significant positive correlation between the 4-hour PCA and its initial 24-hour cumulative morphine consumption. The Pearson R, or the R value, was 0.33, and you see it was statistically significant. Now, if you think back to what do you think that strength of that relationship is? Remember we talked about that earlier. Let me go back to that slide. All right, so a low or weak correlation would be something below between 0.2 and 0.4. Moderate is 0.5 to 0.7, and 0.8 to 0.1, either positive or negative. Those are the strength of those correlations. So if we go back, what do you think that strength of that relationship is? Well, actually, it would be considered low or a weak correlation. So if you looked at that scatter plot, it's probably going to look, I'm not a very good artist here, but it's probably going to have like here's your X, here's your Y, and you're probably going to have some dots that aren't quite, they're sort of going, doesn't work very well, but you kind of get the idea. It's not going to be a perfectly straight line. It's going to be maybe a little bit more scattered, but generally looking like it's going in that direction. It's going to look more like, actually, let me take you back here, probably something more like this when you're looking at it.